This video was originally recorded November 2019 as an exclusive for my patrons on patreon.com. After consulting with my patrons, I'll be releasing some of these videos publicly. Thanks to each of them for their support. Hi, it's Robin. The vast majority of 8-bit computers and consoles used either the 6502 or Z80 processors or derivatives of them. Most of the Commodore, Apple, and Atari machines use the 6502 or derivatives, along with the Atari 2600, the original NES, the Spectrum, and many Tandy TRS-80 computers used the Z80, and the Game Boy also used a derivative of the Z80. And two of the most famous books about these processors were both written by Rodnay Zaks, and I have them here, Programming the Z80 and Programming the 6502. Mr. Zaks founded Cybex, which was a successful book company which he ran until 2005 and then sold it to Wiley. Now today we're going to be talking about Programming the 6502 by Rodnay Zaks. And this here is the 4th edition, which I believe is the final version that he printed. Here is the 3rd edition that looks identical on the cover, but says 3rd edition inside here. And I've got the very 1st edition here, very old school. And this is from, I believe, 1978. Yep. It was given to me by my favorite high school math teacher, Joe Hall. Thank you, Mr. Hall. He was into programming these computers, but around 1990 he wasn't into it, and he knew I was, so he gave me this book, which was a huge boost for me. So I realized that I've never read this book cover to cover. I've certainly referred to it many times over the years, different versions of it, but I've never read it right through, so I've been doing that the last month. And it makes pretty good bedtime reading if you can't get to sleep. But as I was reading through, I got to chapter 5 here, addressing techniques, about all the different kinds of addressing. And in the book, he gives kind of a general overview of processors and these different theories, and then gets specific about the 6502. But I was reading here in chapter 5, this section, a block transfer routine, more than 256 elements, and I actually discovered that there's a bug in the program here. I had to enter it into the Commodore 64 confirm. So yeah, block transfer routine, more than 256 elements. Gives a diagram of how it should work, and then here's the actual program listing and some explanation text. So it's kind of running through this in my head. Thought I found a bug, and I thought, oh no, it was actually very clever. It's not a bug, and I realized, no, there really is a bug in here. So that's what we're going to look at today. So I think we'll look at it in the book first, and then I'll hook up the Commodore 64 here, and we'll go through fixing it. I'll explain as it goes, but I think we need to spend some time in the book first to get a good understanding of it. Now, sorry about these red underlines in the text. I don't know who had this book before I did, but I certainly did underline it. Again, it was the 1st edition that was given to me by my math teacher, and this one I think I found at a used bookstore. Now, I want to point out that this is still an excellent book. I still recommend you read this. It's a good reference, lots of good information in here, and we all make mistakes as programmers. Some of us, our mistakes end up going more public, like me when I mess up on my YouTube channel, or Mr. Zaks in his book here. I don't mean any disrespect to him or his work. I'm mostly surprised that this book, in its 4th edition, would still have the same error, and I checked and it's the same in the very 1st edition. So this bug had been through 5 years, and I believe this book sold extremely well. I think it was even used as a college text, so I'm just very surprised that this bug survived. So if you want a copy of this book yourself, you can find a scan of it on archive.org. Just search for Programming the 6502 if you don't have a physical copy of it. So let's just read through this. If you just want to get to the Commodore 64 part, check the description below, and there'll be an index there so you can jump ahead to that part. A block transfer routine, more than 256 elements. Let's now consider the general case of moving a block which may contain more than 256 elements. we can no longer use a single index register, as 8 bits do not suffice to store a number greater than 256. The memory organization for this program is illustrated in figure 5.7 over here. The length of the memory block to be transferred requires 16 bits, so note that. Well, that's part of the problem here, and therefore is stored in memory, meaning rather than in an index, which can only go up to 255. The high order part represents the number of 256 word blocks. Now notice Zaks often uses word, which is correct. In an 8-bit processor, a word is 8 bits, but a lot of people would use word to mean 16 bits. So that can be a bit confusing. So in this case, I believe in this book, Zaks always uses word to mean the same as a byte. The high order part represents the number of 256 word blocks. The rest is called remain and is the number of words to be transferred after all the blocks have been transferred. So blocks is the high byte and remain is the low byte of the number of words to be transferred. The address for the source and the destination will be memory locations from and to. So we're going to do a block copy from a memory location to another memory location of length blocks. That's how many 256 byte blocks gets copied, and the remaining bytes are going to be in remain. Let us first assume that remain is 0, that we are transferring 256 word blocks. That is, that there's no remainder. It'll be in the 16-bit value, the low byte will always be 0. The program appears below. Let's look at that diagram quickly first. There's a little diagram here. The base, this is the source block, which is pointed at by the from location. And then this destination is going to be 2. And it's going to be copied through the accumulator byte by byte. And we're using the X register to do the copy. I'm actually not sure what the N means there. I guess that's the number of blocks. And here's another diagram of it. From and to the departure area and the arrival area. Memory map for general block transfer. Okay, so we'll read through the source code here. We're going to load the A accumulator with the source low. This is the low byte. This is kind of a funny way of separating the low and the high into separate bytes. I'll show you in Turbo Macro Pro that there's a more efficient way of doing that, but this is a very early assembler, and I think they didn't have that low and high byte operator, which is the less than symbol or the greater than symbol. So first we're going to load the low byte of the source location and store it in memory location from, which is a 0-page address. That means it's in the first 256 bytes of memory. And then we're going to load the high byte and store it also in 0-page from +1. Store the source address is the comment here. Note on Turbo Macro Pro you have to put a semicolon before the comment. Then we're going to load A with the destination low byte. These are immediate modes. They're from labels. And actually, the labels are missing from this. So we're going to see that later, that this program isn't complete. We're going to have to add a little bit more to it to actually make it assemble and run. We're going to load the low byte of the destination, store it in the to address. Then we're going to load the high byte and again store it in 2 + 1. So these have become from is a 16-bit pointer for the source location, and to is a 16-bit pointer to the destination. So we've initialized that. Then we're going to load the X register with the number of blocks to copy, the number of 256 byte blocks, and load Y with 0, the block size. This is where it gets a little bit weird, but we'll go through this. Y is 0, and that's going to be used here in the indirect indexing mode. So here's a label, which is going to be used to loop. Load A from Y. So it's going to look at the pointer, the address in from, and that's using that index indirectly. Say this is location FB and FC in C64 memory, and in those locations, in low byte, high byte format, 0020, then this is going to become location 2000, and then we're going to add the Y register as an offset, an index, which is currently 0. So this is going to load from location 2000. That's called indirect indexing. And then we're going to store it in, say this points to location 3000, 3000 plus 0 in the Y register. So it's just simply going to take a byte from this memory location and store it here. We're going to decrease Y, which seemed a little bit weird to me at first. So that means it's going to copy the 0 byte, but then it's going to decrease Y, which wraps around because it's 8 bits. 0 goes down to 255 or FF hex, the maximum value in an 8-bit value. And if it's not equal to 0, go to next. So this is a little loop that will copy 256 bytes. But a little bit strangely, it does byte 0 first, then it goes all the way up to 255, 254, 253, all the way back down to 1. And then when it gets decreased back to 0, the branch if not equal is no longer true, so it falls through to the next line. So it copies 256 bytes, but does it, instead of copying from 0 up to the top or from the top down, it does the bottom byte and then all the way down again. A little bit strange. I thought that was weird. Now, a lot of the time in 6502 programming, we do decrease Y as an optimization, but in this case, it didn't matter. We could increase Y and still get exactly the same result of copying all 256 bytes in a linear fashion instead of this wrapping around fashion. Anyway, doesn't really matter. It just seemed a little odd to me. Then there's this next section, next block. We're going to increment the high byte of the from location, that's the +1 there, and also of the 2. So now that we've copied, say, page 20, that is location 2000 to 20FF, all the way to 3000, 30FF, then we increment the high byte, because this is stored in low byte, high byte format. This will change the 20 and the 2000 to 2100, and this one from 30 to 3100. So that's correct. Then we're going to decrement X, which is loaded with the number of blocks. So say if we want to copy 16 blocks, which would be 4 kilobytes, this number goes from 16 down to 15. Branch if minus to done, which there isn't actually a done label here, but we'll put one in here at the end. Once we enter this into the C64. So if it's minus, it's using that to check if it's gone into the negative. If it is, it's totally done. Then it checks if it's not equal to 0. So say it was 16. Well, this would be the same as it decrementing to -1 or 255 decimal. So that doesn't happen. If the branch if not equal is next, well, it's not going to be equal to 0. It's just 15. So it's going to do this again. So basically, this is sort of a clever way of getting more value out of that blocks register, but it has a side effect, which he doesn't note, of meaning you actually can't copy more than 32 kilobytes with this, because it's using the high bit as a flag for whether the process is totally done or not. Back here, it talks about how the length of the memory block to be transferred requires 16 bits. It's actually only 15 bits worth of transference using the 16th bit as a flag to handle the remain. So it should be specified in here, and he never does explain that exactly that this is limited to a maximum of 127 blocks. So I think that's a failing in the text. 32K transfer is probably perfectly adequate, especially when you have a maximum of 64K, and back in this day you often wouldn't, but I still think it should be documented here. So branch if not equal to next, and then this is the kind of clever bit, which is also the bug. Load Y with the number of remain. This is actually the low bits. It's copied all the 256 byte blocks it can, and now it's going to do any remaining number of bytes that you want to copy. So if you don't want to copy exactly multiples of 256, this is where it handles it. Load Y with remain, and then it kind of cleverly jumps back to next. And instead of Y usually wrapping around or being reset to 0 each time, it's going to copy a smaller number of bytes. So say you did another 128, like half a page, then this loop would enter with Y being set to 128, or 80 hex, and then it would copy 128 bytes. Or does it? This is the problem. This loop assumes that byte 0 has been copied in the first place, but when you start the loop partway through, like 128, it'll go all the way from 128 or 80 hex down to 1, but then it'll be decremented to 0, and branch if not equal won't be true. It will never copy that last byte. So this is the bug. It will fail to copy the first byte of the final block. Bug! So I'll just read some of this explanation. The 16-bit source address is stored by the first 4 instructions of the memory from. That's right, we covered that. The next 4 instructions do the same thing for the destination, which is stored at address 2. Okay. Since we have to transfer a number of words greater than 256, we will simply use 2 8-bit index registers. That's good. The next instruction loads the X register with the number of blocks to copy, yes, to be transferred. This is instruction 9 in the program. Okay, he hasn't numbered them here, but fair enough. The next instruction loads the value 0 in index register Y in order to initialize it for the transfer of 256 words. Yeah, right there. We will now use indexed indirect addressing. Well, no, we will not. This is an error in the text. I used to get these confused. There's indexed indirect addressing and indirect indexed addressing. And then I realized, actually maybe even from this book, it's whatever order it happens. This is indirect index because first it does the indirection in the brackets, that whatever, this is a pointer, memory location from and 0 page points to another location. So that's the indirection. Then the Y index is added on. But here, indexed indirect is actually when you have the address, comma, X, and that is all inside the brackets. Then it goes to the indirect location, adds the X index in 0 page, and then uses that as an index. It's actually very rarely used. I don't know if I've ever used it in all the 6502 coding I've done. I'm sure it has uses, but it's very rare. This form is much more common. And anyway, it's mixed up here. It should be remembered that indexed indirect will result first in an indirection within page 0, then an indexed access to the 16-bit address specified by the index register. Look at the program. Yes, indirect, indexed. The instruction loads the accumulator with the contents of the memory location whose address is the source, plus the index register's Y contents. Look at figure 5.7 for the memory map. Here the content of register Y is initially 0. Actually don't find this all that helpful. Doesn't even actually refer to Y here. A will therefore be loaded from memory address source. Note that here, unlike in our previous example, we assume that source is the address of the first word within the block. Using the same technique, the next instruction will deposit the contents of the accumulator, the first word of the block we want to transfer, at the appropriate destination location. Store A 2 plus Y. Just as in the preceding case, we simply decrement the index register, then we loop 256 times. I think we decrement it and then we loop 255 times. Anyway, this is implemented by the next 2 instructions, decrease Y and branch if not equal next. Yeah, we loop 255 times because it's already gone through once. Caution, yeah. A programming trick is used here for compact programming. The alert reader will notice that the index register Y is decremented, yes. The first word to be transferred will therefore be the word in position 0. Yep, that's the first one transferred. The next one will be word 255. This is all correct. This is because decrementing 0 yields all ones in the register, or 255 decimal. The reader should also ascertain that there is no error. Okay, there's no error when it's a complete block. Whenever register Y decrements to 0, a transfer will not occur. Yes. The next instruction to be executed will be next block over here. Therefore, exactly 256 words will have been transferred. Clearly, this trick could have been used in the previous program to write a shorter program, sure. Once a complete block has been transferred, it is simply a matter of pointing to the next page within our original block and our destination block. That's what these increments here do. Make it point to the next block. This is accomplished by adding 1 to the higher order part of the address for source and destination. This is performed by the next 2 instructions in the program. Yeah. Next, increment from and increment 2 plus 1. After having incremented the page pointer, we simply check whether or not we should transfer one block by decrementing the block counter contained in X. This is performed by decrement X. Yeah. If all blocks have been transferred, we exit from the program by branching to location done. Okay, we're almost done. Branch minus done. Otherwise, we have 2 possibilities. Either we have not decremented to 0, or else we have exactly decremented to 0. If we have not yet decremented to 0, we branch to location next. If we have decremented exactly to 0, we still have to transfer the words specified by remain. This is the last part of our transfer. This is accomplished by load Y with remain, which loads index Y with the transfer count. We then branch back to location next. So this is what I thought was kind of clever, how he was able to reuse the Y register, like he was able to reuse this code by inserting a different value of Y in. But as he points out here, when the register Y decrements to 0, a transfer will not occur. It needs to be done upon entry into this routine, which does not happen in the final block. The reader should ascertain that during this last loop where the branch instruction to next will be executed, the next time we re-enter next block, we will indeed exit for good from this program. This is because the index X had the value 0 prior to entering next block. The third instruction of next block will change it to -1, and we will exit to done. So yeah, when X is decremented one more time here, then it is done. All right, so now we've gone through that. Let's hook up the C64 and try this out ourselves. Okay, I've got my Commodore 64C set up here, and I'm using my Super Snapshot cartridge, mostly just for the monitor, and I have it plugged into an Expander 3 cartridge expander, and that's just for the reset button. The C64 doesn't have a built-in reset button. If you've got a real Commodore 128, 128D, they have a reset button built in, or if you've got a C64, some people make modifications to it, or some cartridges have a proper reset button built in. The Super Snapshot has a soft reset button. If you hold Commodore and press this button, it will sometimes reset, but not reliably. So an actual hardware reset is a good idea. I haven't used it much yet, but this Epix Fast Load Reloaded does have a monitor, and that's a reset button built in, so that's an inexpensive solution. The monitor in the Epix Fast Load's a little bit, I far prefer the Super Snapshot one, but it's okay. It certainly does quite a bit. It just has a different syntax. That's a little weird. So I'm just going to load up Turbo Macro Pro here. I'm not using the REU version this week. It's not necessary, and actually it's a little simpler for this kind of thing. But anyway, you can download the D64 from a link in the description. And I've got these various block copy source files on here that are different versions of the source code as I work through them. So it's sys32768 to start it. And we'll load in block copy 1. Okay, and here's the source code. As it says, exactly as book. So I just typed in the source code without the comments directly in here. But if we go to assemble it, back arrow 3 to assemble, and you see all these undefined statements. Those are all the missing labels. So back arrow load, block copy 2, and I'm putting the origin to 900 hex. That's kind of arbitrary. 0801 is where your basic code would normally live. This is assembly, and the object code can live really at almost any place. So I'll put it at 900, but that's what this star equals. It's the origin of the code. And I've gone through and added labels source low. I want the block's source location to be 1000. So the high byte is going to be this 10 hex, and the low byte is 0. We've split it into 2. I'll show you how to improve that later. Again, the destination address is 2000 hex, which we've split into a high byte and a low byte. This is just to follow the way Zaks did it, probably because of the limitations of his assembler back then. I had mentioned 16 blocks that we're going to copy. I've decided 4 is a better number. It's just it's easier to prove that it's working with a smaller number of blocks. So we'll use 4, and we'll start off with our remaining bytes of 0. And the from and the to are 0 page locations. This requires 2 bytes each. So from is actually FB for the low byte, and then FC for the high byte. And 2 is FD and FE. I think I mentioned earlier that on the C64 these addresses are always available for the programmer. Okay, so that fixes all these problems, all those assembly errors that we had, because these labels are all now defined. And these are just like constant integers. They're not actually variables. The assembler just substitutes. When it sees source low, it puts 0 in that place. And the number sign means immediate mode, like load a constant, load an actual number instead of from a memory location. And the one other thing we had to fix is this done label is missing. So we've added that in here, done, and then return to subroutine. Okay, so we can assemble this with back arrow 3, and it shows it successfully assembled. And then we can press S to exit to basic. Now if I reset and go into the monitor, Shift F8 is a shortcut for that. If you're using Vice, you can look up the Vice documentation how to get into the Vice monitor, which is very similar. In some ways it's more powerful, but also not quite as user-friendly. Then we can just look at the code that was assembled to location 900. Here it is. You can see that it's storing 1000 into the high and low bytes and so on. This is the same code. And just to look at location 1000, right now it's just full of garbage. So we're going to fill from location 1000 to 1FFF with whatever byte. I like using BB. And we're going to fill the destination location from 2000 to 2FF, just fill it with zeros. And now we can look at memory at location 1000. You can see there that's full of BB. And we'll look at location 2000. That's full of zeros. And now we will run our program at 9 times 256. That's what 900 hex is equivalent to 9 times 256 decimal. And there, it ran. It went and executed our machine language program and returned to basic. Now it can pop back into the monitor, and we'll look at location 2000 and see that location 2000 is now filled with BB instead of 0. And we told it to transfer 4 pages worth. That is 400 hex bytes, 1024 decimal bytes. So that successfully transferred 400 bytes right up to 23FF, and then starting at 2400, it's still what we initialized it to as 0. So that's working exactly how we want it to. Now we can re-enter the modder with sys32768. There's our code. Now let's just change the remain to say copy 8 bytes more. So 4 full pages, and then another 8 bytes. And we will assemble that. And back arrow 1 also exits to basic. This actually disables the super snapshot instruction, so I'm just going to hit reset and F8 to pop into the monitor. And now if we look, location 1000 is still full of the BBs. Let's fill the destination with zeros again. And execute 9 times 256. And we'll take a look at what it's done. F1 is a shortcut down to the bottom corner. Modder 2000. So now it's full of BBs. Yes, this is a bit tedious, even 4 pages, but we'll scroll down. And what has it done? Okay. So here we see what it's done. It's copied a solid block of BBs for 400 hex bytes. Then it left this one blank, 0, like we showed in the bug, and then copied 8 more. It actually did that in reverse. It actually started here at the 8th, 7, 6, 5, 4, 3, 2, 1, and then once it was decremented, once that index was decremented, the Y index, to 0, it was done and left this byte blank. So actually it's copying 1 more byte than we want, and it's offset by 1. It's not copying the byte. So that's pretty buggy. So let's try and fix that. Okay, now I've loaded in block copy 3, and I've done some cleanup here. Let me show you what I've done. Now we've got 16-bit addresses for the source and the destination. And the way you do that, well, it's simple here. Just instead of source low and source high, we've combined it into a single source label. And then down here, after the immediate sign, a less than symbol gets the low byte of the 16-bit label source. So this takes the low byte, and this greater than symbol takes the high byte. And it saves all that pretty ugly source low and source high having to split up into 2 pieces. And we've done the same with the destination. And I've even done the same thing with the length here. Instead of having a number of blocks and then a remainder, I've turned that into a 16-bit address as well. Actually, I'll change that to 0408 just to match how we used to have 4 blocks. And then now we're going to try and copy 8 remainder bytes. Okay, and otherwise the code should all be the same. Just looks tidier. Okay, let's try running that. And I'll reset. Go into the modder, we'll fill from 1000, again with the BB. And we'll fill from 2000 to 2FF with 0. And we will sys to 256. And we'll look in the modder and just make sure that the bug is the same. Yeah, there it is. Same thing. Okay, and now we'll load up a final fixed copy. So big thanks to my patron csbruce and also my friend Adrian Gonzalez for helping with this fix. In the original version of this video, my fix actually had a bug, and csbruce pointed that out. So I'm recording this new section just to go through my new fix of the fix. So people in glass houses and all that. Again, all respect to Mr. Zaks. The lesson here is that 6502 code can be tricky. Okay, and so the various fixes that we've done, I've kind of combined a few here. First of all, I've added comments on the lines I've added to that previous version of the code. Here we're just going to check if the high byte of the length is 0, then that means we have less than a full page to copy, and we're just going to branch ahead to remain down here. I added this label as well. So that allows this routine to copy less than a full page, because I didn't like how you had to copy at least a full page plus. Then the next bit here is from Adrian Gonzalez, who suggested starting the Y register at the top of the 256 byte page, and then each time we decrement Y, instead of using the 0 flag that's automatically set by the decrement, we're instead going to compare Y to FF hex to see if it's wrapped all the way around. Then we can detect that, and that allows us, instead of doing that strange copying the 0 byte and then going all the way down, now we're just going to copy in a linear fashion right from the top all the way to the bottom. Now, this does take a couple more cycles per loop, so it is a little slower, but it works. Okay, and then the next change we made here was to, well, just adding that remain label so we could branch ahead, skipping the full page copies, and then checking if it's equal to 0. That means there's no remainder. That is, if the low byte of the length was 0, 0, it was just full pages, then there's nothing more to be done, and we have to check for that. Now that's thanks to csbruce for that, because I had missed that check in my original version, and it would copy, if you tried to copy exactly, say, 2 pages, it would actually copy 3 pages. In one of 256 cases, it would copy an extra 256 bytes. So, yeah, thanks to csbruce for noticing that. And then, after getting the length of the remainder, we pre-decrement it by 1, and that prevents us from copying that 1 extra byte that we saw earlier. So the original version would copy 1 beyond the range of what we wanted. So that's corrected here. And that's it. Now it works. So we can go up here and change the length. So it now even supports 0 bytes copied. So we'll try a transfer of 200 hex bytes. Back arrow 3 to assemble. Hit the reset button. And we'll fill memory from 1000 to 1 FFF. Actually, we can do this. 1, 2, 3, 4. It'll fill memory with that repeating sequence. You want to see that? Memory 1000. So just in case you didn't like filling with BB, some kinds of bugs could be undetected when we just fill memory with 1 byte. So instead, I'll just fill it with that repeating sequence. And then fill from 2000 to 2FF with just 0, clear it out. We'll exit. We'll call 9 times 256 our routine. Pop back into the monitor, and we'll take a look at 2000. 1, 2, 3, 4. And there we go, right up to 21FF and zeros. I tried several other combinations. Again, the D64 will be available for download in the video description. So if you want to try this out yourself and see if there's any other bugs or any other improvements you can make on it, I welcome that. Okay, and just to change that length to 408. Again, we'll assemble. We'll fill 1000 again. And we'll make sure 2000's cleared out. Back in the monitor. And we'll look at the result here. And there we go. This time it's filled in properly from 2400 to 2407. It hasn't bled over by one bite, and that's not 0 anymore. So that's working. All right, thanks very much to my patrons for their support of this channel, including this video that was originally an exclusive for, well, about 10 months now. And I've been talking to them about this, that I'll be making these videos available after at least 6 months have gone by. If you want to see them as they debut, then check out my Patreon page. Hey, thanks for watching, and we'll talk to you next time. A 1, 2, 3. When people need some trouble, Ball Swiper and his team go on the elevator. They see there is trouble. They go down the side. They hop into their vehicles. Now they go driving to save the day. They drive to City Hall. There was Fire Barf there and his minions. Oh yeah, the minions were attacking. A bad guy taking someone, but Ball Swiper didn't let him take. Not so fast, Fire Barf. What? How did you get here? You should eat more food if you are going to be bad. Is that how strong you are, Fire Barf? Looks you are too powered up. It is electricity time. So maybe if Rodnay Zaks makes a 5th edition of Programming the 6502, he can use some of these suggestions.